Welcome to our first episode on nanomaterials and nanotechnology. In this session, we will explore how nanotechnology, which seems like a modern field, has roots that go back thousands of years. You will see how ancient civilizations unknowingly harnessed nanotechnology to create stunning artifacts, medicines, and tools. And now we will also give the overview of the modern nanotechnology and their use. I am Dr. Samrat Sarkar, Assistant Professor of Physics. So let's begin. Now, the brief contents of my talk is, first will be the introduction of nanomaterials and nanotechnology, then the terminology and definition of nanomaterials, classification of nanomaterials, quantum confinement, surface area to volume ratio, various types of nanomaterials, their properties, some novel materials, and concluding remarks. Now let us discuss about the chronological events in the development of nanotechnology. Now, as far as 4th century BC, the Romans used nanoparticles unknowingly, and they used in stained glass such as the Lycurgus cup. Then in the 9th century, the Mesopotamians also prepared Damascus steel. So they knew the technology of making steel and other alloys, and they used carbon nanotube like structures. In the Middle Ages, then gold and silver nanoparticles were also used for staining glass. Then in the modern times, the 1857 Michael Faraday synthesized colloidal gold. Then in 1931, a major invention which pushed the boundaries of nanomaterials and nanotechnology was the discovery of electron microscope. With this discovery, people now could see the nanostructures, and thus the field of nanomaterials and nanotechnology took a new impetus. After that, there were rapid progress in this field. For example, in 1959, Richard Feynman gave his seminal talk that there is plenty of room at the bottom. In 1974, Norio Taniguchi first coined the term nanotechnology. Then in 81, the scanning tunneling microscope was invented by Rohrer and Binnig. In 1985, the C60 football-like Buckminster Fullerene was discovered. In 1991, carbon nanotubes were discovered. And very recently in 2004, just 20 years ago, graphene was isolated, and it gave the Nobel Prize in 2010 to Jain and Novoselov. And now the present date, nanotechnology have lots of application in medicine, in cosmetics, in sports, in energy research, and quantum computing. Now, this is the nano age. We can briefly divide the age after the 1800s into 4 parts. During the 1800s, with the Industrial Revolution, up to about 1890, it was the mechanical age or the age of mechanical machines. After that, some basic electronic materials consisting of vacuum tubes were discovered, and we came to the electromechanical age. So it was the combination of the basic electronic devices and the machines. After that, the real electronic age came with the discovery of the transistors. And after 2000, it can be said it is the nano age. Now, ancient nanotechnology. The ancient nanotechnology, as I discussed previously, that the Romans, they knew this type of use of nanoparticles. They didn't know the actual science, but the alchemists used various type of metallic nanoparticles for staining glass. And this is the picture of that Lycurgus cup. Now this cup is made of a special type of glass which contains gold or silver nanoparticles, and it is very interesting that the glass looks greenish color on reflected light, but in transmitted light it looks red. Then this we can see that a solution containing colloidal suspension of nanoparticles having different color. Now the interesting thing is this all the liquids, they are chemically similar. They consist of the same chemical compound, the nanoparticles, they are suspended in the liquid, but they exhibit different colors. That is due to some nano property known as the quantum confinement. Now we will discuss quantum confinement later. Now range of the fields for nanotechnology. Now in which fields nanotechnology are used? So nanotechnology have application in nanomedicine, nanobiotechnology, nanolithography. Nanolithography means to manipulate at very small scale and to manufacture small structures by actual manipulating the atoms. It can be photolithography or electron beam lithography. Then nanoelectronics, electronics at the very small scale. Nanomagnetics, nanorobotics, which is a very new field, and much progress is being done with the advent of artificial intelligence. Then biomedical devices and MEMS and NAMES, micro electromechanical system and nano electromechanical systems. Now with the progress of nanotechnology, the research in nanotechnology has grown by leaps and bounds. The number of publication on nanotechnology was very less during the 1970s, 80s, 90s. So it was basically the small amount of publications were done, since the field of nanotechnology was not well known. It was just some material science and chemistry. But after the 1900, it saw a gradual increase, and it was very rapid up to about the 2000. And then beyond the 2000, it took an exponential rise in the number of publications. So nowadays, the number of publications in the nano field is well beyond 10 to 20,000 per year. There is plenty of room at the bottom. This was a famous statement given by Richard Feynman, a Nobel laureate. Now, this statement was given by him in a talk at Caltech in December 29, 1959. Now, the meaning of this statement is that we can explore and do much fundamental research and application in the atomic scale. So, during that time, there was no technology at the very miniature scale, and he said that we can do much. There is much scope to be done in the small scale of things. Now, let us come to the meaning of nanomaterial. Now, what is nanomaterial and what is nanotechnology? Now, the word nano comes from nanometer, because the materials whose length scale lies in the region of nanometer are called the nanomaterials. And more specifically, any material or particle whose size at any dimension lies between 1 to 100 nanometer are called the nanomaterials or the nanostructures. And all types of technology and application with these nanomaterials are collectively called as the nanotechnology. Now, the concept of nanotechnology was introduced by Richard Feynman, but the actual term nanomaterial or nanotechnology, it was given by Norio Taniguchi. Now, let us see the scale of matter, and we can understand how small the nano range is. Now, let us come to the macro scale. Here we see that the 10 centimeter or the meter, it is our macroscopic scale, human scale. We can see that a shrub or a leaf approximately lies in the sub-meter level. Now, as we go down to the centimeter or the fraction of a centimeter, we come to the scale of the ants, dust mite. If we go far below, then the human hair, and then the plant cells, and ultimately we reach the micro region, where there are the animal cells, some zinc sulfide microspheres, or many other types of microstructures. If we go much below that, then we come to the bacteria, the RBC, then we enter the nanoscale. The nanoscale have been represented by the size of the virus, the DNA, and ultimately we come to the amino acids and the molecular scale. So this is truly the nano region. Here we can see the hexagonal honeycomb lattice of graphene. So starting from this centimeter to this nanometer, so it is about 10 to the power minus 8 to 10 to the power minus 9 factor smaller. Now, terminology of nanomaterial, I have already covered that the materials whose at least one dimension is less than 100 nanometers are called the nanomaterials or nanostructures. Now, obviously the question comes, why nanomaterials are important and why do we study? What is the fundamental reason? It is due to various properties that comes up when particles are reduced into the nano dimensions. Now, nanomaterials are of great interest because, as I told, that many new properties emerge, and these new properties are the unique optical, magnetic, electric and other physical and chemical properties of the nanomaterials, which are much different from the bulk. Now, another important property is the size to volume ratio and also the quantum effect that becomes predominant at this small scale. Now, example, silver foil does not react with dilute HCl. We have seen that the dilute HCl cannot react with the silver foil, but if that silver is in the form of the nanoparticles, then it can easily react with even with dilute HCl. Then gold and silver both are chemically inert, but the nanoparticles show catalytic as well as antibacterial property. We know that the gold is a noble metal and silver is also not very reactive, but the nanoparticles are highly reactive. And also gold nanoparticles, they show different colors, and that is due to some new quantum effect or the effect of the nanoparticles. Let us classify the nanomaterials. Now, nanomaterials can be classified on various parameters. Now, we will classify nanomaterials based on the dimensionality. Nanomaterials can be 0-dimensional, 1-dimensional, 2-dimensional and 3-dimensional. Now, let us describe each of these types of materials in a little detail. 0-dimensional nanomaterials. Now, dimensionality of nanomaterials means how the charge carriers, that is the electrons, or if in semiconductors the electrons and the holes are confined. Now, 0-dimensional means these charge carriers are confined in all direction. So, they are confined in all direction means no dimension is free, and so they are called the 0-dimensional nanomaterials. Now, they are basically small particles or dots or point-like structures. Various types of nanoparticles, the nanograins, the nanoshells, nanorings, then the fullerenes. Fullerenes are the cage-like carbon spheres, and quantum dots. These are the 0-dimensional nanomaterial, and they have various type of applications in biomedical imaging, cancer treatment and optoelectronics and quantum computing. So, we can see here the TEM images of various nanoparticles. We can see here that these are actually quantum dots. We can see that the size of this nanoparticle is less than 10 nanometer. Quantum dots are the special type of 0-dimensional nanomaterial, and their size is well below the Bohr excitonic radius. We will come in detail what is Bohr excitonic radius in the coming slides. Now, let us come to the 1D nanomaterials. Now, 1-dimensional nanomaterials are the materials in which the charge particles or the charge carriers, they can move freely in one dimension. So, they are elongated structures like various type of nanowires, then nano whiskers, nanotubes, and carbon nanotube is a very good example. Now, they are basically structures with very high aspect ratio, that is their length is much larger than the other dimension like the breadth and the thickness. Now, application: nanowires can be used in electronics and PN junctions, and they are also used as logic gates and data storage. Now, let us discuss about the two-dimensional nanomaterials. Now, the 2D nanomaterials are basically the materials which are sheet-like, means the charge carriers can move freely in 2 dimension. And a very good example is graphene and various type of sheet-like nanostructures of transitional metal sulfides such as MOS2, WS2, etc. Now, other types of nanomaterials in 2D are the nanofilms, nanolayers, then nanocoatings, and they are basically thin films or very ultra thin films consisting of a single atomic layer or a few atomic layer. Now, they have applications in energy storage, lasers, then infrared imaging, energy harvesting and thermoelectric device. They have such a lot of application because they have a very high surface to volume ratio. And some of these two-dimensional materials are popularly called as quantum wells. So here we see the actual TEM image of the graphene, and we can see this is the honeycomb structure of graphene, and these are other TEM images of various type of sheet-like structures. Now, 3D nanomaterials. Now, 3D is peculiar. In 3 dimension, by the definition we have given, it means bulk. That is, the charge carriers are not confined. They are free to move in all the available 3 dimensions. So, 3D material can be bulk and they can also be nano. So, what are 3D nanomaterials? 3D nanomaterials on outside they look like bulk, but inside there are nano features. For example, various type of porous structures which have nanopores, then nano channels within it are the 3-dimensional nanomaterials. The examples are various type of porous carbon, then the metal organic frameworks, covalent organic frameworks, they are called the 3-dimensional nanomaterials. Now, here in a single picture we can see the 0D, 1D, 2D and 3D. So, these are the structures of fluorine, then the core shell, yolk shell structure. These are the nanoparticles or in 0 dimension. These are the 1-dimensional tubes, filaments, etc. 2-dimensional sheet-like structures, nanosheet, porous sheet, nanoplates, and these are the mesoporous structure, and they are having internal pores, then frameworks are there, nanostructure assembly, metal organic framework. So, these are the 3D nanomaterials which are distinct from the 3D bulk. Now, a very important property of nanomaterials, that is quantum confinement. Now, what is quantum confinement? Before understanding this thing, we have to understand what is confinement. So, confinement, as I discussed in the various type of low dimensional structures 0D, 1D, 2D, it means how the charge carriers are confined in a particular dimension. Now, when there is a restriction in the movement of the charge carriers, that is called quantum confinement. Now, if this confinement is extreme, then it is called quantum confinement, because now quantum mechanical effects occur when the charged particles are not allowed to move freely. Now, in quantum confinement, there is an important parameter, that the size of the structure or the particle, they should be less or comparable to the Bohr exciton radius. The Bohr exciton radius is the average distance between an electron and a hole in an electron hole pair, which is called the exciton. Now, in quantum confinement effect, the density of states of the structure, the nanostructure, is not same as that of the bulk. Now, density of states. The meaning of density of state is the number of energy states. The number of energy states per unit energy per unit volume of a material. The energy states are present in the energy band, and that is called the density of states. Now, in bulk, when there is no restriction in any dimension, then the density of state is proportional to the square root of the energy, and so the relation between the density of states and the energy is parabolic. So mathematically we can say that the density of state is proportional to root over of E, that is the energy, and so the relation is parabolic. But in two dimensions, which are called the quantum well, now suppose this is the z axis, this axis is in the nano level, and so the electrons are confined in this z axis, and so they are the two-dimensional materials, and in this case the density of state changes and there is no dependency on the energy, it remains constant. So up to a certain range these are constant, then there is a step. So this one and this one and this one, these are the density of state is independent of the energy, and we get a different density of state versus the energy relationship. Now in one dimension, when there is confinement, suppose in both two dimension x and y, only one dimension is free, the electrons can move freely in one dimension, then the density of state is inversely proportional to the square root of the energy. So we can say DOS is proportional to 1 by root of E, and in that case the relation is like this. There are e to the power minus half is like this curve, and we get a distinct this type of density of state. And in zero dimension, when there is confinement in every direction, the density of states are reduced to delta functions, and the delta functions means they are the spikes. So we get spikes, and this represents that the band structure is now reduced to discrete energy levels, and this occurs in quantum dots. And since in quantum dots there are energy levels and not energy band, so they are also called the artificial atoms, because they are represented by energy levels which are discrete and which they are similar to the isolated atoms. Now quantum confinement. As I discussed that in quantum confinement the size of the particle is comparable to the Bohr exciton radius. Now what is the result? What we can observe due to this effect? Now we can see here, as we discussed that in quantum confinement effect the band structure is reduced to discrete energy levels, and we can see as the size of the particle reduces, the discretization is more and more, and the result is the increment in the band gap. So the bottom of the conduction band and the top of the valence band, they become larger, the energy gap becomes larger, and if the band gap increases, then the excitation and the emission of electrons will be comparable to those photons which have the increased band gap, and as a result the wavelength emitted by those photons which make transition from the conduction band to the valence band will be decreased, or they will shift to higher energies, and that shift is called the blue shift, because the red photon and the blue photon have a higher energy, and so if there are some nanoparticles, the size of the particles are different, so there will be emission of different colors of photons, and this, due to the confinement effect, the same solution containing the nanoparticles, they can show different colors due to fluorescence, and we can see there is a gradual change in color and that is the blue shift due to the reduction in particle size. Now this is the enlarged diagram that I was discussing from bulk to nano, and how the band changes to the discrete energy levels, and it results in the increment of the band gap and blue shift of the emitted waves of light. Now let us come to the surface area to volume, and this is a very important ratio in case of nanomaterials. Now we know that as we decrease the size of a particle, the proportion of atoms that are exposed to the surface are larger. For example, let us consider a big sphere. Then if it is a big sphere, then the number of atoms inside which is not exposed would be larger. But as we decrease the size of the particle, proportionately more number of atoms will be at the surface. So what happens? The surface area to volume ratio will increase as we decrease the size of the particle. So we can also show it mathematically. Now let us consider a sphere of radius r. So what is the surface area of the sphere? It is 4 pi r square, and the volume is 4 by 3 pi r cube, and so the surface area to volume ratio, if we do the calculation, it becomes 3 by r. That means this ratio is inversely proportional to the radius. Now if we decrease the size of the particle, so the s by v, that is inversely proportional to r, will increase. And due to this increment in the surface area to volume ratio, more exposed surface means more surface reactivity, more catalytic activity, and also the materials can show enhanced other surface effects like microbial activity, and also some speeding up of reactions in which the nanoparticles are used as catalysts. With this, I conclude the first episode of this topic of nanomaterials and nanotechnology. So we will be back soon with the next topics. So for that time, stay tuned. Thank you.